Nobody in this room knows why gravity works. Not one of you. And before you get offended, I want to be very precise about what I mean by that, because most of you have been told at some point in your education that we understand gravity. You were told about Newton, maybe you were told about Einstein, maybe you're one of the people who can write down the Einstein field equations from memory, and you think that means you've got this one handled. You don't. Neither do I. And I've been working on this for over 4 decades. Here is what we actually know. We know how gravity behaves. We can predict it with insane precision across distances spanning billions of light years. We can calculate the wobble of a pulsar 25,000 light years away and be right to 7 decimal places. We can describe the bending of light around a galaxy cluster so precisely that we use those bends as telescopes. We call it gravitational lensing, and it is one of the most beautiful things in science, the universe using its own curvature to show us things that would otherwise be invisible. We can do all of that. What we cannot do, what nobody on this planet can do, is tell you in the deepest sense why mass creates gravity at all, why anything should curve space, why the geometry of the universe gives a damn about energy. That is the question I want to put in front of you today, not a dressed up version of it, not a comfortable, cleaned up textbook version that makes it look more solved than it is. The real question in all its uncomfortable openness. Because if you're going to spend an hour of your life in this room with me, you deserve the real thing. Let me start from the beginning, not from Newton, from before Newton, because the first thing I want to demolish is the idea that before Newton, people were just confused idiots who thought the Earth was the center of everything and hadn't figured anything out yet. That story is wrong, and it's condescending. Aristotle, for instance, had a coherent and internally consistent theory of why things fall. He was wrong, but he was wrong in a sophisticated way, and understanding how he was wrong tells you something important about how we get things wrong today. Aristotle's idea was that objects have a natural place in the universe. Earth is heavy, so it belongs at the bottom, and bottom meant the center of the cosmos. When you drop a rock, it's not being pulled anywhere. It's going home. It has a tendency, a nature, an intrinsic orientation toward a place. And here's the thing, that idea is not crazy. It is an attempt to explain a genuine observation using the conceptual tools available. The rock falls. Why? Because it wants to be at the center. That is a causal story. It's wrong, but it's a story. What Newton did, and this is the moment I always want students to sit with longer than they do, is he replaced the story with an equation. That is not nothing. That is not a small move. The equation was precise, universal, and terrifying in its implications. The force of gravity between two objects equals the gravitational constant times the product of their masses divided by the square of the distance between them. F equals G, m1, m2 over r squared. Every student in this room knows that formula. But Newton himself was perfectly clear about what that formula did not tell him. It told him how strong gravity is. It told him how it scales with distance. It told him nothing, zero, about how it works. How does the sun reach across 93 million miles of empty vacuum and tug on the Earth? Newton called this action at a distance, and he hated it. He wrote in a letter to Richard Bentley in 1693, and I am going to quote this because it is one of the most honest things ever written by a great physicist, that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He discovered the law of gravity, and he didn't believe his own theory was a real explanation. That is intellectual honesty of a very high order. So Newton gave us the rules. He didn't give us the reason. And for about 200 years, nobody could do better. The rules worked so well that people mostly stopped asking for the reason. That's a psychological trap that science falls into all the time. Precision of prediction is so satisfying that it can crowd out the drive to understand mechanism. You can calculate so well that you forget you don't understand anything. Then comes Einstein. And now here is where it gets strange. I mean, genuinely strange. Not strange in the way that popular science books say things are strange, where strange is just code for different from what you're used to. I mean, strange in the way that when Einstein showed his finished theory to colleagues in 1915, some of the best minds in the world looked at it and had a reaction that was essentially, this cannot be right because it is too bizarre. And Einstein's response was essentially, I know it's bizarre, but the math is forcing my hand. The core claim of general relativity is this: gravity is not a force. It is the curvature of space-time. Mass and energy curve, the geometry of the four-dimensional fabric of space and time. And what we experience as gravitational attraction is simply the tendency of objects to move along the straightest possible paths, what mathematicians call geodesics through that curved geometry. You are not being pulled toward the Earth right now. You are being guided along a curved path through space-time that happens to terminate at the floor. Now, I want to be very precise here because this is the point where analogies usually start cheating. The rubber sheet analogy, you've all seen it. You put a heavy ball on a rubber sheet, it creates a depression, a smaller ball rolls toward it, and someone says, that's gravity. And every physicist in the room groans. Not because the analogy is useless, it's not useless, but because it is secretly circular. The smaller ball rolls toward the depression because of gravity. The analogy uses gravity to explain gravity. The curvature in a rubber sheet only does anything if you're already in a gravitational field. So let's throw that analogy out and do this honestly. What does it actually mean for space-time to be curved? Let's build this up from scratch. Start with a flat piece of paper. Draw two parallel lines. They stay parallel forever. That is what flat means, geometrically. Now take that piece of paper and wrap it into a sphere. Now those parallel lines, what used to be parallel, converge. They meet. Lines that started out going in the same direction end up at the same point. The geometry has changed. And that change has consequences for how lines' paths behave on that surface. Now replace the surface with four-dimensional space-time. Replace the lines with the trajectories of objects moving through time. When the geometry curves, trajectories that started out going in the same direction, objects that started with the same velocity, end up converging. They end up moving toward each other. That convergence is what we call gravity. But here is what the analogy on the sphere still gets wrong. On a sphere, the curvature is purely spatial. It's a two-dimensional surface embedded in three-dimensional space. And the curvature lives in the spatial directions. What makes general relativity so much stranger is that the most important curvature, the curvature responsible for ordinary, everyday gravity, the gravity that makes apples fall in planets' orbit, is primarily curvature in the time dimension, not in the spatial dimensions. When a massive object is sitting there, what it mainly curves is the flow of time in its vicinity. And the reason objects fall toward it is that when you are in curved time, moving in any direction at all, even just sitting still, you are actually tracing a path through space-time because time keeps passing. And the straightest path through time curve geometry happens to point toward the massive object. Let me make that concrete. You are sitting in your chair right now. You feel stationary. You are not stationary. You are moving through time at the rate of 1 second per second, which sounds trivially true, but is actually the whole ballgame. Your trajectory through space-time is mostly in the time direction. The Earth's mass has curved the space-time around you, specifically by making time flow slightly slower near the surface than it does farther away. This difference in the rate of time flow, this gradient, is what creates what you experience as gravitational acceleration. You are trying to move along the straightest possible path through space-time. That path, in curved time, curves toward the Earth. This was verified experimentally, by the way, not theoretically experimentally. In 1959, Pound and Rebka at Harvard dropped gamma rays down a 22-meter tower and measured the blue shift as the photons fell into a slightly deeper gravitational well and experienced slightly faster time. The experiment confirmed the time dilation prediction of general relativity to about 1%. Later, experiments with atomic clocks on aircraft confirmed it to much higher precision. The GPS satellites in your phone include corrections for gravitational time dilation. Without those corrections, your navigation would drift by about 10 kilometers per day. General relativity is not an abstract philosophical position. It is running in your pocket right now. Now, let me tell you where I personally got tangled up on this, because I think it's instructive. When I was first working seriously through the implications of general relativity, and I mean working through it technically, not just reading the popularizations, I kept asking myself the same question in the wrong way. I kept asking, how does mass tell space-time to curve? And I was imagining this as a mechanical process. Mass is sitting there, and it reaches out somehow and deforms the space around it, like a finger pressing into clay. I was thinking about it causally in a way that assumed a pre-existing flat space-time that then gets dented. That picture is wrong, and it took me an embarrassingly long time to see why. The relationship between mass energy and space-time curvature in general relativity is not like a finger pressing into clay. It is more like, and this analogy is also imperfect, but it cheats less the relationship between temperature and heat distribution in a material. You don't say that the hot region reaches out and deforms the temperature field around it. The temperature distribution and the heat sources are parts of a single unified description. Mass energy and space-time curvature are not two separate things in an action and reaction relationship. They are two aspects of a single geometric reality described by the Einstein field equations. The equations say, essentially, the curvature of space-time described on the left side of the equation equals 8 pi g over c to the fourth power times the distribution of energy and momentum in that space-time described on the right side of the equation. The geometry and the matter are locked together. They co-determine each other. Change the matter, you change the geometry. Change the geometry, you change how matter moves, which changes the geometry again. It is a self-consistent, mutually determining relationship, not a one-way causal story. A mathematician I respect deeply, Roger Penrose, who has one of the most ferocious geometrical intuitions of anyone alive, once described the left-hand side of Einstein's equations as the most beautiful object in theoretical physics, and the right-hand side as a pile of garbage. What he meant, affectionately but precisely, is that the right-hand side, the stress-energy tensor, bundles together all forms of energy, momentum, pressure, stress, into a single mathematical object. And in some sense, we're just saying, whatever matter does, its gravitational effects are captured by this tensor. The left-hand side is gorgeous differential geometry. The right-hand side is a kitchen sink. And the mystery is, why are these two things equal? Why does geometry couple to energy and momentum at all? Why not to something else? Why not to the cube of the energy? Why not to the color of the object or its temperature? Why is it energy momentum that curves geometry? And here is where it gets strange for the second time. The answer, in one sense, is the equivalence principle. Einstein's great insight, the one he called the happiest thought of his life, was this: there is no experiment you can do inside a closed box that will tell you whether you are in a gravitational field or accelerating in empty space. If you are in a rocket accelerating at 9.8 meters per second squared, everything inside that rocket behaves exactly as it would on the surface of the Earth. Not approximately, exactly, to any measurement, with any instrument, at any precision. Gravity and acceleration are locally identical. This principle, the equivalence principle, is what forced Einstein toward the conclusion that gravity must be geometry. Because if gravity is geometry, if it's the curvature of space-time, then you can always locally transform it away by going into a free-falling frame. And free fall is just acceleration. So the equivalence holds automatically as a consequence of the geometric picture. The equivalence principle doesn't just motivate the geometry explains why the equivalence principle is exactly true, not just approximately true. But now ask the deeper question. Why is the equivalence principle true? Why should inertial mass, the mass that resists acceleration, the mass that appears in Newton's second law, F equals ma, be identical to gravitational mass, the mass that generates and responds to gravity? These are logically separate things. One is about resistance to change in motion, the other is about coupling to the gravitational field. Why should they be the same? Newton assumed they were the same and never explained why. Oetvers tested it experimentally at the end of the 19th century and found them equal to about 1 part in a billion. Modern experiments have pushed this to 1 part in 10 to the 13th power. They are equal. But why? In general relativity, you don't answer this question so much as absorb it. The fact that gravity is geometry means the distinction between inertial and gravitational mass collapses. There is only one kind of mass, and it is both the thing that resists acceleration and the thing that couples to curvature, because those are the same thing. But this feels to me like the question has been elevated rather than answered. Why is there a kind of physical quantity that simultaneously resists acceleration and couples to space-time curvature? What is mass, fundamentally? And this brings us to the Higgs field, which I want to handle carefully, because there is a version of this story that gets told in every popular article that is technically true but deeply misleading. The Higgs field, discovered, or rather confirmed in 2012 with the detection of the Higgs boson at CERN, is responsible for giving mass to certain fundamental particles. The W and Z bosons, which mediate the weak nuclear force, acquire their mass through interaction with the Higgs field. Quarks get their current algebra masses through Yukawa couplings to the Higgs. Electrons get their mass the same way. The mechanism is called spontaneous symmetry. Breaking the Higgs field has a non-zero value everywhere in the vacuum of space. And particles that interact with this field experience a kind of drag, a resistance to acceleration that we interpret as inertial mass. Here is where the misleading version usually appears. Popular accounts say the Higgs field gives particles their mass, and mass is what creates gravity. So the Higgs field is why gravity exists. And this is wrong in a subtle but important way. First, most of the mass in your body does not come from the Higgs mechanism. Your body is made of protons and neutrons. Protons and neutrons are made of quarks and gluons. The quarks themselves get modest masses from the Higgs, but the bulk of the proton's mass, about 93% of it, comes from the energy of the strong nuclear force binding quarks together, not from the Higgs. Through E equals mc squared, the binding energy of the gluon field contributes to mass. The Higgs gives you the small residual quark masses. The big number comes from QCD, quantum chromodynamics, the theory of the strong force. So your mass is mostly stored energy of the strong nuclear interaction with a relatively small Higgs contribution. Second, and more importantly, even if we fully understood where mass comes from, we still wouldn't know why mass couples to space-time curvature. Those are different questions. The Higgs answers, why does this particle resist acceleration? It does not answer, why does anything curve the geometry of the universe? I want you to feel how deep that open question actually is. It is not a gap that's waiting to be filled by some missing calculation. It is a question about the structure of our most fundamental framework. In general relativity, the coupling of mass energy to space-time curvature is simply postulated. It is built into the theory as an axiom. Why is it true? We don't know. There are speculative frameworks, string theory attempts to derive it from a more fundamental picture. Loop, quantum gravity approaches it differently. There are theories where gravity is emergent, where it arises from thermodynamic or information theoretic principles that are more fundamental than space-time geometry itself. I have colleagues who believe that gravity is not a fundamental force at all, but an entropic effect, that it arises from the tendency of systems to maximize entropy in the way that Verlinde and others have explored. I am not convinced, but I am not dismissing it, because the question of why gravity exists at all is real, and it is open, and anyone who tells you we've got this one solved is either confused or lying. Now here is where it gets strange for the third time, and this is the part that I find most genuinely, productively unsettling. The three other fundamental forces, electromagnetism, the weak force, the strong force, have all been successfully described in the framework of quantum field theory. They are quantum theories. They obey the rules of quantum mechanics. They're force-carrying particles, photons for electromagnetism, W and Z bosons for the weak force, gluons for the strong force, have been detected and studied in detail. They exist in a world where energy is quantized, where uncertainty is intrinsic, where fields fluctuate at the quantum level. Gravity does not. General relativity is a classical theory. It does not play well with quantum mechanics. When you try to quantize gravity in the same way you quantize electromagnetism, you get nonsense infinities that cannot be renormalized, predictions that make no physical sense. The theory breaks down. It breaks down precisely at the scale where quantum effects should dominate the Planck scale, at distances of about 10 to the minus 35 meters and energies of about 10 to the 19th GeV. At that scale, space-time itself is expected to become quantum, to fluctuate, to lose its smooth geometric character. And we have no complete, consistent theory of what happens there. This is not a small gap in our knowledge. This is arguably the central unsolved problem in theoretical physics. The unification of general relativity and quantum mechanics, the theory of quantum gravity, would be the deepest achievement in the history of science. We do not have it. We have candidates. String theory is the most elaborately developed. Loop quantum gravity is a serious alternative. There are others, but none of them has made a prediction that could be tested with current or near future experiments, which means we cannot yet say which, if any, is right. I spent decades working on aspects of this problem, on the connection between gravity and quantum information, on the black hole information paradox, on the question of whether space-time itself is built from quantum entanglement. And the more I worked on it, the more I became convinced that the reason gravity is so hard to quantize is not a technical accident. It is telling us something deep about the nature of space-time, that it is not a smooth background fabric on which physics happens, but something that is itself emergent, itself built from something more fundamental, something we don't have the right conceptual vocabulary to describe yet. The black hole information paradox is the place where this tension becomes most acute, and I want to spend a moment on it because it is directly relevant to our question, and because it was the site of one of the great intellectual battles of the last half century, and I was in that battle. When Stephen Hawking showed in 1974 that black holes radiate, that they emit thermal radiation due to quantum effects near the event horizon, now called Hawking radiation, he established that black holes have a temperature and therefore an entropy. The formula for black hole entropy, derived by Bekenstein and Hawking, says that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is bizarre. For any normal physical system, entropy scales with volume. The entropy of a gas in a box is proportional to the size of the box. But a black hole's entropy scales with the surface area of its boundary. This suggested, and I want to be careful about the word suggested here, because this is genuinely not yet proven, that the information content of a three-dimensional region of space might be fully encoded in the two-dimensional surface surrounding it. This is the holographic principle. The battle I was in, the black hole war as it's been called, was over the question of whether information that falls into a black hole is destroyed when the black hole evaporates. Hawking said yes. The thermal radiation that comes out carries no information about what went in. The information is lost. This would violate a fundamental principle of quantum mechanics, which says that information is always conserved, that the laws of physics are in principle reversible, that you can never truly destroy information. I said, no, the information must come out somehow, encoded in subtle correlations in the Hawking radiation. Hawking thought I was wrong. We argued about this for about 20 years. In 2004, Hawking conceded. He announced at a conference in Dublin that he now believed information is not lost, that black holes do eventually return all the information that fell into them, encoded in the outgoing radiation. He was right to concede, and I give him full credit for having the integrity to do so publicly. But the reason he conceded is not that we had solved the problem. The reason is that Developments in string theory, specifically the ADS-CFT correspondence, which relates a theory of gravity in a higher dimensional space to a quantum field theory on its boundary, strongly suggested that black hole evolution must be unitary, must preserve information, because the boundary theory is unitary by construction, but the mechanism by which information escapes is still not understood. We know it must happen, we don't know how. And this matters for our question about gravity, because the black hole information paradox is at its root a problem about what gravity is at the quantum level. It is telling us that the smooth space-time geometry of general relativity and the quantum mechanical principle of unitarity are in tension, and something has to give. Either space-time is not as smooth as we think near the event horizon, or quantum mechanics has to be modified, or there is a deeper framework that reconciles both, and we don't have that framework. There is a beautiful idea that has emerged from thinking about this, which I want to put in front of you because it connects directly to our central question. It is the suggestion increasingly taken seriously by a significant number of theorists, including people whose judgment I respect greatly, that space-time geometry itself, including the curvature that we identify with gravity, is built from quantum entanglement. The idea, associated with work by Maldacena, von Ramsdonck, Swingle, and many others, is that the connectivity of space-time, the fact that different regions of space are near each other in a geometric sense, is related to the degree of quantum entanglement between the degrees of freedom in those regions. If you remove entanglement, space-time falls apart, distant regions become disconnected. Entanglement is the glue that holds the geometry together. If this is right, and I want to emphasize the if, because this is still a research program, not an established theory, then the answer to why does mass create gravity would be, at the deepest level, something like mass energy affects the quantum information structure of the underlying degrees of freedom, and space-time geometry, including its curvature, is an emergent description of that information structure. Gravity would not be a fundamental force. It would be a collective, emergent phenomenon, like temperature, like pressure, like the elasticity of a solid, real but not fundamental, arising from something deeper. I find this idea genuinely exciting, and I also find it genuinely terrifying in the way that the best scientific ideas are terrifying. Because if space-time is emergent, if it's not the fundamental bedrock, but an approximate description that breaks down at some deeper level, then the question, why does mass curve space-time, becomes why does mass affect the information structure of the underlying thing? And we are back to staring at an open question, just at a deeper level. Maybe that's progress. Maybe we've lowered the floor, or maybe we've just moved the mystery to a new address. Let me bring this back to something concrete, because I don't want to leave you with only abstractions. Think about a neutron star, a city-sized ball of matter, roughly 1.5 times the mass of the sun, spinning up to several hundred times a second, generating a gravitational field so intense that a mountain on its surface could not be more than a few millimeters high. Anything taller would be crushed by the tidal forces. The curvature of space-time near a neutron star is extreme enough that light itself is bent significantly as it leaves the surface. We have measured this. We have detected gravitational waves from neutron star mergers, including a merger in 2017 that was also seen in gamma rays and optical light, GW170817, one of the most spectacular events in the history of astronomy. We watched two neutron stars spiral toward each other, losing energy to gravitational radiation, exactly as general relativity predicted, collide, and produce a kilonova that synthesized gold and platinum and uranium and scattered them into the galaxy. The gold in your wedding ring, if you're wearing one, was probably made in an event like that somewhere in the history of the Milky Way. And the space-time curvature generated by those merging neutron stars rippled outward at the speed of light for 130 million years and made the mirrors of the LIGO detector move by a distance 20 times smaller than the diameter of a proton. That is what gravity is in operation, not a force reaching across space, a ripple in the geometry of the universe itself propagating like a wave on the surface of reality. When I think about the fact that we detected that we built instruments sensitive enough to measure a displacement 20 times smaller than a proton and used it to watch two dead stars merge 130 million light years away, I have a feeling I can only describe as the same feeling I had when I first understood what general relativity was actually claiming. Not awe in a soft, comfortable sense, something sharper than that. The sense that the universe is built in a way that is far stranger and far more specific than anything we would have guessed, and that we are somehow improbably beginning to read it. But we are not done reading it. We are not close to done. We do not have a quantum theory of gravity. We do not understand what happens at the Planck scale. We do not know whether space-time is fundamental or emergent. We do not know why inertial mass equals gravitational mass at a level deeper than, because the equations work out that way. We do not know why the gravitational constant has the value it has, why gravity is as weak as it is, a puzzle known as the hierarchy problem, which remains stubbornly unsolved. We do not know whether the dark energy that is currently accelerating the expansion of the universe is a cosmological constant, a dynamical field, or a hint that general relativity breaks down at cosmological scales. We do not know whether gravitons, the hypothetical quantum carriers of the gravitational force, exist as particles in the conventional sense, and if they do, whether they could ever in principle be detected. These are not embarrassing admissions. They are the honest inventory of an active, living science. The embarrassing thing would be to pretend otherwise. And here is the thing I most want to leave you with. The fact that we don't have the final answer is not a sign of failure. It is a sign that the question is hard enough to be interesting. Every time in history when physicists thought they had reached the bottom, that they understood the basic structure of reality, the universe turned out to have another floor below the one they were standing on. Newton thought he had mechanics. Maxwell thought he had electromagnetism. In 1900, Lord Kelvin thought physics was essentially complete. And then quantum mechanics arrived, and everything changed. And then general relativity arrived, and everything changed again. We are not at the end of this process. We may not even be at the beginning of the last chapter. The question, why does mass create gravity, is at the moment answered at several levels and unanswered at the deepest level. At the level of observable phenomena, mass creates gravity because objects follow geodesics in curved space-time, and mass energy is what curves space-time according to the Einstein field equations, which have been verified to extraordinary precision by every experiment we've been able to run. At the level of mechanism, the curvature emerges from the relationship between the stress-energy tensor and the space-time metric, mediated by the equivalence principle, which ensures that gravity is indistinguishable from acceleration and therefore must be geometric. At the level of quantum foundations, we don't know. We have candidates, we have speculations, we have hints from black hole physics and holography and entanglement that something very deep is going on, but we don't have the theory. So you came in here maybe thinking you were going to get the answer to a question, and in some sense I've given you answers, layers of them, one below the other. But in another sense, I've walked you to the edge of a very deep hole and showed you that we don't know how far it goes. That is not a failure of physics. That is what physics looks like from the inside. And the question is whether that unsettles you or excites you or both. Because for me, it has always been both. The fact that I can spend 50 years working on something and still not know the answer is not comfortable, but it is what keeps me working. If we knew the answer, there would be nothing left to argue about. And an argument with no opponent, no resistance, no possibility of being wrong, that isn't an argument. It's a monologue, and monologues are boring. The universe has been arguing with us for about 14 billion years. Every time we think we've got it pinned down, it shows us another card it was holding. Right now, it is holding several: dark matter, dark energy, quantum gravity, the arrow of time, the nature of information, the reason for the particular values of the constants of nature. It is holding these cards and watching us with something I can only describe anthropomorphically, I know, as patience, or maybe amusement. Figure it out, it seems to say. I'll wait. And I think we will figure it out. Not because we're smart, we are, but the universe doesn't care about our smartness, but because we are persistent, because we build better instruments, because we ask better questions, because every generation of physicists inherits the wrong answers of the previous generation and uses them as scaffolding to reach something truer. Newton was wrong about gravity being a force. He was also right about so much of the math that Einstein couldn't have gotten to general relativity without him. Einstein's theory is almost certainly not the final word, but it will be part of the scaffolding that the next theory is built on. The question of why mass creates gravity will be answered. Not the way I have answered it today, not at the level of geometry and geodesics, though those answers are real and important and not going anywhere. At a deeper level, at the level of what space-time actually is, what mass energy actually is, and why the universe insists on coupling them together in precisely the way that it does. When that answer comes, if I had to guess, it will come from the direction of quantum information theory and quantum gravity, from understanding what space-time is made of at the Planck scale. It will be the biggest thing in physics since quantum mechanics. Bigger, maybe. I won't be here to see it. That's fine. The work is what matters, not who gets credit. But you might be. Some of you in this room might be. And if you are, when that answer comes, I want you to remember this afternoon, and I want you to remember that the answer was available all along, hiding inside the question. And the reason it took us so long to find it was not because we were stupid, but because the question was pointing at something real. And real things are hard, and hard things are worth it. Don't let anyone tell you this part is simple. It isn't. And now you know exactly why.